Hello and welcome to the video lecture series on contact mechanics in the course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements here at Luleå University of Technology. And now this is the first part of the second video lecture on contact mechanics on modeling and simulation. And this is a recap of what we learned in the previous lecture on contact mechanics fundamentals. Nothing added to the recommended literature with this part, but it's the course compendium, chapter 4, and K.L. Johnson's book if you want to go into real details on it. So the outline of this video will be first a recap on the contact mechanics problem, and then how to discretize it. And we do that step by step by considering the domain and the gap between the surfaces, then the deformation, and then the force balance equation, and then the whole contact mechanics problem is formulated in a discrete form. We will also discuss a little bit about numerical accuracy. It is time to sum up, so we will have a look at the full discretized 1D contact mechanics model, and then a little bit about accuracy and how to discretize in 2D. So, the recap. Contact mechanics problem is formulated as a complementarity problem, where either the deformed gap is zero and the pressure is positive, obviously, or where the deformed gap is positive, there is no pressure, pressure is zero, and the deformed gap is formulated by the gap between the undeformed surfaces with the deformation added, and then interference of rigid body movement delta. And the elastic deformation equation is given by sort of Boussinesque's ID because of the normal traction consideration of the boundary condition on the half space. And then we have the force equilibrium, which just states that the pressure that builds up, the resulting pressure in the contact zone, must balance the applied load. And we have independent variables, just the x1 and x2 variables in 2D, or x1 in 1D. And then the dependent variables, which are mainly p, but the u, the deformation u, and the deformed gap between the surfaces can be seen as implicitly dependent variables, auxiliary dependent variables, and then depending on how we pose the problem, if we give the interference or if we use the force balance, force equilibrium and force balance equation with the applied load, delta, the interference, may be a dependent variable too. So the input parameters in all cases are the undeformed gap between the surfaces, the elastic moduli of the two bodies, and the Poisson ratios, of course. And then it's either the load, the applied load W, or the interference delta, depending on how the problem is posed. In the previous video, we also made the problem non-dimensional. And we did that by introducing a number of reference parameters for the independent and the dependent variables. When we did, we obtained the dimensionless representation of the problem, which in general form can be expressed like this. Well, on the surface, it doesn't look any different at all when you consider the complementarity problem, except for capitalized letters for the dependent variables and a small bar of the non-dimensional interference. But there are a slight difference in the expression for the non-dimensional deformation and force balance equations, in that they now contain these groups of reference parameters which are dimensionless groups of of reference parameters. And we have three of them, and we also recall that we can choose the reference parameters more or less arbitrarily. Of course, we need to consider that they have to have the same dimension as the variable that we want to scale. And of course, it's quite wise if we choose them in relation to the problem at hand.